All right, now we're going to go ahead and break down each of these 6 steps in a few more videos to complete out the primary structure part of the module. Okay, so step 1, we separate the chains. Now, the subunit interactions, and when we say subunit interactions, we're saying separate polypeptide chains interact with each other typically through weak forces, non-covalent interactions like hydrogen bonds and ionic interactions, van der Waals, and even the hydrophobic effect is in effect. Okay, so they can be separated using pretty gentle denaturing techniques. Those reagents that are used in step 1 are reversible. They can be dialyzed away and you can restore the folding of your protein. Okay, so in order to use denaturants, we can't use SDS because remember, no protein is recovered. Once you add SDS, it's stuck forever. All right, so we're going to be using different denaturants, and they're listed below in red. These are to add to your toolbox. You can use extremes of pH to disassemble. In fact, this disassembles the heavy and light chain of antibodies, extremes of pH. You can use chaotropic agents, urea or guanidinium hydrochloride. These 2 reagents act to eliminate or decrease the hydrophobic effect by competing with the hydrogen bonds of water so that your protein no longer needs to bury the hydrophobic groups away from water. That's how they're thought to act. So they're gentle denaturants that can be dialyzed away. And in some cases, a high salt concentration, now here we're talking about small ions, sodium and chloride, can actually denature the separate polypeptides in a multi-subunit protein. In step 2, if you still have polypeptides connected, then you would need to add a denaturant. Now, how would you know you have polypeptides connected? If you ran an SDS page gel in the presence and absence of the reducing agents DTT or beta ME, and you had one large protein in the absence of reducing agent, and then in the next lane, you have 2 separate proteins, 2 or more separate proteins in the presence of a reducing agent, then you know you have a disulfide bond, okay? And so that's what's happening in step 2. We're going to reduce the disulfide bonds. Reducing means gaining electrons. Remember, oil rig, oxidation is losing, oil, reduction is gaining, rig. So we're going to have to gain electrons and pick up protons from solution to give back those sulfur groups at the end of the cysteine side chains, their hydrogens, okay? And that's what is done with beta ME and DTT. They break the disulfide bond by giving back those hydrogens. Okay. The problem comes when you want to prevent reformation of the disulfide bond. If you stopped here, then there's really nothing keeping your disulfide bonds from reoxidizing or reforming their disulfide bond. And so what we need to do is we need to prevent disulfide bond reformation somehow. And we do that by a step called alkylation. Alkylation is a generic term for adding carbon-containing atoms that weren't there before. And the way we do that is with iodoacetate or iodoacetic acid. I-O, the O is the oxygen, A-C, that's the acetate part. Iodoacetic acid has an excellent leaving group, the iodine, and the alkylating group is the acetic acid. Okay, so let's have a look at what that actually looks like. In the first step, and you don't need to memorize this reaction, you have 2 polypeptide chains connected by an intermolecular disulfide bond. The sulfurs are green, and each sulfur comes from the cysteine side chain of the opposite chain. Now, by adding a reducing agent, such as beta ME, sometimes called 2-mercaptoethanol, don't memorize the structure, you actually give the electrons back and the protons to give you a hydrogen on each of the sulfurs, reforming the cysteine side chains independently. And then the oxidized product is the disulfide bonded beta Me. Again, it's not the reaction that I'm interested in you knowing. It's the fact that this is what a reducing agent does. It reduces the electrons here are actually going to become 2 electrons, one from the hydrogen and one from the sulfur, to give you a covalent bond with that. I think I've explained it. Okay, so that works also with DTT. So either beta Me or DTT can be used at this step to reduce the disulfides and break that bridge that way. However, this arrow is reversible, and these could go back this way if you don't somehow block them from doing so. And that's what we're going to do on the next slide. We're going to add iodoacetate, which is whose form structure is shown here, but you can call it IOAC. That's what most people call it. And iodoacetate irreversibly alkylates, forms a covalent bond here at this sulfur in order to prevent it from being reactive. And what it makes is an S for sulfur, carboxymethyl cysteine. You don't need to memorize that, but that's what this is. The sulfur is now in the middle between 2 carbons, just as it is in the methionine side chain. And remember, the sulfur in the methionine side chain is not reactive. And that's essentially what you've done here, but in this case, not just with a methyl group, but with an acetate group. And there's our leaving group, the iodine, which leaves with the hydrogen. Okay, so that's the reaction that is combined with your reducing agent to give you the breakage and irreversible alkylation to prevent disulfide bonds. Okay, so this is irreversible and prevents reformation of the SS disulfide bond. All right, so make sure you understand that reaction and add iodoacetate and DTT and beta Me to your toolbox for step 2.